Hi, in this video we are going to study about a very interesting theorem, that is a divergence theorem, and these theorem have many applications in the physical field, physical applications in every field, in physics, chemistry, in electric field, engineering field, in every field. Without this divergence theorem we can move. Okay, so in order to define these vector field, first of all we need a capital F, that is a vector field, that is mi plus nj plus pk, and we need a closed surface S in this, right? And S is a closed oriented surface. Oriented surface means this is a closed surface. Closed means everything is closed in this, all points lies in between this, and this is oriented means given orientation in this, given normal vector field with this. Okay, given orientation, an orientation together with a unit normal vector field together with a surface is called an oriented surface. Right, it is positively oriented or negatively oriented. We can orient that. This is the outward orientation, and we can also use the inward orientation also. This is the inward normal, and this is the inward normal. Right. So, in order to define these divergence theorem, we need a certain knowledge about flux. What was flux in this? Right? Flux is the flow rate per unit area. There is a flow rate per unit area. There is a flow rate per unit area through a medium. Through a medium. Through a medium. Okay, and what is this? We need this type of figure, that is means this is along a closed surface. Yes, f dot n ds, or this can be written as double integral over s f dot ds. Okay, this is a vector field, right? So, what is the meaning of this one? This is a closed surface. What is this means? This means the total flux, total outward flux. Actually, this is outward flux. Flux of vector field F across a closed surface. Closed surface, yes. Okay, and this theorem says that double integral over a closed surface S f dot n ds. This is the outward flux, and this is a outward flux of a vector field, and which is same as what? Which is same as the triple integral over a domain D del dot f into dv. Del dot f dv. Del dot f means this is a div f into dv. This is a divergence integral. This is the divergence integral. This theorem says that this double integral over S, consider a vector field, right? Vector field on a closed surface S, right? It is in 3 dimension. Then we can say that the outward flux means there is suppose this is a surface in this. This is a 3-dimensional surface, right? Consider a small region, that is a ds. Okay. Consider the unit normal n, and this is a vector field f. Okay. This is a vector field f, and f dot n, this is a ds, small ds, there is small area in this. And this f dot n ds means this is a outward flux on this small area, right? Count this total, consider this total surface area, that is suppose divide these infinitesimal region into a small rectangles, a small cubes like that, like this way. Here there is a cube like region, and I can draw, this is okay, one more cube here, I need one more cube, one more cube in this. Here this is a flow, actually this is a flow. Suppose a fluid is entering through this region, through the surface, and this pass through this region, and corresponding to this this rectangular cube type region, through these surfaces, this is going outward, right? But this is going, this vector is the going outward corresponding to this region, but corresponding to this region, this vectors are the incoming vectors, right? So the total flow rate per unit area, we have to calculate this total flow rate through the surface. This is a incoming vector, this is outgoing vector, right? Incoming vector and outgoing, corresponding to this surface. There's here this vector, consider this surface, consider this vector corresponding to this surface, this is an outgoing vector corresponding to this region, this is an incoming vector. So the flow rate, actually one is corresponding to this is it is negative, and corresponding to this region this is positive. So when we are adding these flow total flow together, this flow corresponding to these phases, the phases get cancelled each other, because this flow vector is corresponds to the outgoing, at the same time incoming flow, right? Incoming vector. So this get cancelled. So when we are adding all these flow rate along a like this closed region, right? First of all, divide these whole region into small cubes like this region, small cubes, and corresponding to this region, and fluid is entering into the solid, and this is going outside, right? Going outside. Consider this fluid, water is flowing in through this pipe, there is fluid is entering and fluid is leaving the region, right? So in this region, divide this into small cubes like region or rectanguloid, okay? And this region, and in total sum all the flow rate along these regions, right? And after summing these, okay, that is, after summing these, we can say that this is the flow rate is, we can calculate this, the sum is actually the flow rate along the surface only, not included this inside region flow rate to get cancelled like these region, like these, okay, that will get cancelled each other, right? At last, when we are calculating this flow rate along the double integral over S, f dot n ds means that is a outward, that is a along the surface only, not inside region, right? Okay. Okay. And in this divergence theorem, this is says that the double integral of the closed region over s f dot n ds, f is a vector field, is equal to the triple integral over d del dot f into dv, del dot f into dv, right? And in this del dot f, this is a divergence actually. The divergence, this divergence can be calculated. This del dot f is equal to, that is how much vectors, this is the meaning of that, how much vectors are diverging away from this vector field, diverging away from this vector field, that is a del dot f. Okay, there is a divergence, right? This del dot f can be positive and negative, right? Suppose this is a surface and this, right? So this is a vector field like these vector field. In this type of vector field, all the vectors are inward normal. Okay, using the inward normal, this is a representation in this. So no vectors are going outside, that is diverging away from this vector field. So here del dot f is always less than 0. Okay, in this type of vector field, this is going, sorry, this is going outside. In this type of vector field, there is del dot f is always greater than 0. Okay, what happened to these type of, suppose this is a region, okay, this type of flow, this fluid is flowing in this region type of, this here also the divergence is happening, divergence is greater than 0, but in this case divergence is more compared to this type of flow. Okay, this flow has a greater divergence, and this is compared to this is very less, right? And this is a meaning of this divergence theorem. Double integral f dot n into ds is equal to the triple integral del dot f into dv, and also we can calculate this as, this is a del dot f is equal to, there is a limit, actually there is a divergence, how much it diverges, that is we are going to calculate. So limit dv, that consider a small volume, dv tends to 0, double integral f dot n into ds divided by the total volume, that is dv, unit volume. This is a total flux, how much of the divergence per unit volume. This is a divergence per unit volume in this, right? So actually this is a total flux, this is a total flux, okay, total flux, this is a total flux per unit volume. Okay, so for the whole volume, this is defined as double integral f dot n d is equal to triple integral del dot f into dv. Okay, this is the meaning of, these are the meaning of this divergence theorem. Okay, in the next video we can discuss about the problems, more problems from this area. Okay, thank you.